Okay, hello everybody. Welcome to track TC6, Mars Research Operations Habitat. Our speaker for this is Carl Greenbaum. And Carl, when you're ready, you can start.
Thank you, Ian. Welcome everyone to my presentation. I spent most of the COVID lockdown working on a design concept for a 24-person moon base that I submitted to the Moon Society as part of their design competition. And quite astonishingly, I won second prize. So thus emboldened, I have evolved the concept to suit a 6-person Mars base. And I'd like to show that to you now, complete with the obligatory tortured acronym of Crew Habitation, Research, Operations, Meals, and Exploration, the Chrome base. Now, obviously, much as in the case of the moon, you want to go where there's water because it's important for resource utilization and in particular for return propellant in many scenarios. Yesterday, the team that did the subsurface water ice mapping research gave a fascinating presentation about how they combined data from 6 different orbiters to develop a composite picture of where the best chances of finding near surface water was. And the criteria for landing site include things like we'd like it in the northern hemisphere where elevations are lower and have a little more atmosphere to help make landing a little easier. You don't want to get too far north to optimize the use of solar power, and it would be nice if there wasn't anything to run into during the landing procedure. But obviously, water ice is the secret, important for all the reasons stated. So they went through that, and they came up with 2 suggested locations that would be suitable for both the landing criteria as well as high probability of significant volumes of near surface ice. One of them was everyone's favorite Mars landing place, Arcadia Planitia, and this one, Deuteronilus Mensae, is one that most people hadn't heard of before. It's a little further south than the Arcadia Planitia, and it seems to satisfy a lot of the criteria from the various missions in terms of water. And as I always like to joke, anything that has Mensa in his name must be a smart choice. It turns out that this is what the area looks like up close. And of course, Mensae doesn't have anything about organization of smart people. It's Latin for table. And so that's a desirable attribute for any place you're going to land. Right now, by my reckoning, SpaceX's Starship is the only spacecraft in development that's going to be capable of conveying large masses of cargo to the Martian surface and also landing. So absent any major surprises, that's what we're going with. And I was amused perhaps at the fact that even a year ago, long before even SN5 was flying, there was a Starship user's guide, so you could design your payload to squeeze into their 9-meter fairing. So the Chrome base, the basic configuration is 4 inflatable modules that will comprise the base, and there'd be each one for crew living space, one for the operation of the base and to support scientific research. There'll be a meals aquaponics facility, and that was the subject of the presentation I did in TC1, and I'll summarize it here, as well as another module for water and gas processing. The meals, the aquaponics facility is going to require about 80 square meters, and it would be nice that all of them could be the same. So the nominal size is 8 by 10 meters. configured like this. The big yellow circles are rotating heliostats. I'd like to save as much power as possible, and even though the sun's a bit dimmer out at Mars than it is around Earth, we still get over 90,000 lux, and typical office illumination levels 500 lux. So it only takes a steerable heliostat on the order of a couple or a few square meters to be able to distribute light and get, you know, office level lighting. There's cask lighting and grow lights for the aquaponics facility is a separate kind of issue. Now, I mentioned these are inflatable modules, and this is the construction sequence. Step one is to excavate a 1 to 2 meter deep foundation, depending on the how hard and how difficult it is to get through the regolith. And then you want to center the area. I'll talk about how we do that a little later on, to form a nice foundation. Spread the habitat bladder and then cover it with 2 meters of regolith and some polyethylene sheeting, which will both hold it, help hold the regolith in place, as well as provide additional radiation shielding. The original concept had, I was going to use some of those roll-up solar panels that they recently installed on the ISS to generate part of the power. It turns out that it's a relatively small fraction of the needed power on these habitat buildings, and so we probably wouldn't go ahead with that part of the design. Now, excavating and then moving 2 meters of regolith over the bladders is not a job for a shovel, but it turns out that NASA, you know, has a pretty good handle on this. This is their Chariot Rover prototype, and they have even prototyped a bulldozer blade to level the regolith and to push some of it around. It's called the Lunar Attached Node for Construction and Excavation. Talk about tortured acronyms, but it's just the tool you need for constructing these inflatable modules, and it'll be used later on in the mission for sintering perhaps roadways, as well as a microwave heating system that'll be used to extract water ice. So here's the crew habitat. It's fairly roomy. There's no sense in being really cramped, but it's adequate space for six rooms, shared lavatory space. And all of these habitat modules, you know, because it's a low angle Quonset hut kind of configuration, the top and bottom edges here are quite low, and so that space is allocated to environmental control equipment and storage, both on either side. At each end, there's an airlock and regolith cleanup space to avoid introducing too much regolith into the living quarters. Now, each of the rooms looks kind of a lot like a small cruise ship cabin. Some of the features that you don't find on a cruise ship are dwarf fruit trees and a fish tank. There are, you know, benefits aside from the fruit and the fish of having these in the rooms, and in particular, the fish these are going to be fry. This is going to be the small fish as they're starting to grow. I elected not to configure it for larger fish, primarily because I didn't want to take the chance that the inhabitants would kind of become attached to the fish, begin to see it as a pet, and be unwilling to harvest it for food. So they grow little ones, which are less likely to become pets. Every cabin needs a window, but you really can't see too well through 2 meters of regolith. But a big, 1.5 meter, video screen, TV screen, fed from some external cameras that can be steered, can provide external views, as well as providing system data and interior camera views as well. And there are numerous studies that have been done recently that talk about the benefits of having plants and fish tanks in the workplace. Increased productivity, cleaning the air, we'll have clean air hopefully, just general improved well-being and stress reduction. And I expect we would have these benefits and in the Mars base as well. One of the cited improvements is reduction in absenteeism, and hopefully that won't be an issue. Research and operations, same basic infrastructure configuration with operating stations for communications and workstations related to base operations, as well as ample room for scientific instrumentation and operations. The Aquaponics facility has a total of 75 square meters of vertically stacked hydroponics trays, as well as a 15 cubic meter fish tank to grow the tilapia. And the blue circles are the sump and the filtering system. And of course, the aquaponics has two components. The hydroponics part, growing the fruits and vegetables. There's lots of choices for vegetables and fruits. They have various, preferred ranges for temperature and pH, but in general, people have found that you can find a compromise environment where they thrive and grow well. pH in particular, the plants are happy at 6.5 or below, and the fish are happier at 6.5 or 7 and above. So you got to strike a compromise there. And as far as temperature is concerned, if the habitat is kept at 22 degrees, which is the typical ISS temperature, then they can accommodate most of these plants. Now, the most efficient technique for growing hydroponics is called the nutrient flow technique, NFT, and it's illustrated in the top photograph, where there are these PVC channels where the water pumped from the sump flows along the channel and soaks the roots of the plants and provides nourishment to those roots, while there's still room in the root structure for the air to get to it to provide oxygen to the roots, which is also important. And that's a valuable combination and promotes rapid and healthy growth. The only limitation to that technique is that because the growth channels are pretty small, you can't grow root vegetables or things with large root masses in those narrow channels. But so to support that, the lowest level in the hydroponics beds will be illustrated. It'd be called a media bed, and it's illustrated in the bottom photograph. Those little brown spheres are expanded clay pellets, and they have large water holding capacity, and they obviously will kind of rearrange themselves to make room for growing tubers and other things. So with a system like this, we can pay homage to Mark Watney and grow potatoes on Mars. On the aquaculture side, I've selected tilapia as the principal fish. They grow quickly, they have a mild flavor, and they tolerate a wide range of water quality. They also have a remarkable food conversion ratio. There are, they're like beef cattle and things like that have food conversion ratios. That is to say, how many pounds of food does it take to grow 1 pound of beef, of up to 20 to 1. Well, tilapia, food conversion ratio is in the order of 1.6 to 1.8 to 1. So much more efficient in converting food into protein. Some of the other choices are possibilities. The other most commonly grown aquaponics, aquaculture fish are trout and salmon in terms of market demand, but you'll notice they're all low temperature, cold water fish, and they don't grow very fast. The reason they're grown on terrestrial systems is that they have a high market price. Another possibility, another fast grower, is the last one listed there. These giant freshwater prawns, thrive in appropriate temperature range. They grow quickly. Unfortunately, they grow when the eggs hatch. They go through a larval stage. Excuse me, and the larvae are a little finicky, and it's kind of fiddly to get them through the larval stage before you can grow them into these giant shrimp, as illustrated here. Maybe for some future configuration, but certainly not the place to start in terms of the fish. Now, this is kind of more of a process diagram than a floor plan, but the water processing module will, take the harvested water and provide some of it, filter it, and provide it directly for use in the base. The bulk of it will go through the electrolysis processor. The oxygen made available for crew breathing. Most of it will be liquefied and stored as potential rocket oxidizer. And the hydrogen from the electrolysis goes into a Sabatier process, which draws CO2 in from the Martian atmosphere. And that combination is used, creates methane, rocket fuel, as well as some more water, which goes back to the electrolysis loop. And I just noticed I need to apologize to Nobel laureate Paul Sabatier for misspelling his name on the diagram. So we talked about finding a place where there's water, but can we get to it? On the left-hand side is the now iconic photograph from the Phoenix lander. They dug their scoop into the regolith, and just a few centimeters down there was ice, and that was an exciting find. But Phoenix was at a pretty high latitude. We'd rather not go quite that high. The diagram on the right is an estimated ice depth map, and the green, the bluish green, that range, that's ice that's estimated to be 5 to 10 or 15 centimeters below the surface, and that's accessible without without a lot of pain. Now, you could try to dig it up, and we could put an excavating arm on that Chariot Rover, but digging up all that regolith is going to put a lot of dust in the air, and if the ice is really hard, it becomes really difficult to dig into it. My preference would be to heat it up like it was in a microwave oven and drive out the water, the water ice, as sublimated vapor, and capture it and use it in that form. Take a bank of microwave antennas, high gain antennas, and the graph on the left shows the penetration depth for lunar soils, lunar regolith, of 0.5, 2.5, and 10 gigahertz. When you're mining for ice, you want to use the lower frequency, get good depth penetration, and liberate as much, sublimate as much water as you can. But if you use the higher frequency, all that microwave energy is constrained to the top levels because there's very little penetration, and what's going to happen is that the regolith is going to melt. And if you go slowly, the regolith will melt, and then it will kind of smooth out and solidify, and you can create a nice smooth surface with some amount of load-bearing capacity. It'll be fine for the surface under the bladder. It remains to be seen whether you could center what amounts to a roadway between the landing pad and the habitat, but you know, that's still currently an unknown. But if you take the Chariot rover, you add a collection tent over the top and a cold trap trailer to capture all the sublimated water vapor, and you drive it around, and the thing operates on batteries, which are readily recharged, and you can take that ice back and process it for all the purposes that we described previously. So there's a lot we know about how to create a livable situation on Mars, but there's obviously a lot that we don't know. The radiation levels and dosages are still have some uncertainty. The dust and associated perchlorates are obviously a concern. If you want to at least initially avoid going the nuclear power route, you're going to need quite a few solar cells, and the mass of the necessary cells is an unknown, as well as how much water vapor is actually going to be available, and what kind of methalox production rate do you need in order to make the system function and have the necessary propellant when it's time to go home. Now, during my research, I found some information about a couple of these issues that I found really interesting, and I want to mention these as I wrap up. Dust abatement is certainly an issue. It certainly was on the moon when we were there, and there's no reason to expect it'll be a better situation on Mars. This paper cited below, two of them, describe a system that uses a matrix of thin spiral wires in the spiral wires are implanted in the material, and they energize it alternatingly with shifting fields, and it generates electrostatic and electrophoretic forces which move the dust around. You know, it sounded okay when I read the paragraph, but then I got to this figure. I took a 10 by 10 centimeter solar panel and illuminated it and got a couple of volts out of it, and then they covered the solar panel with lunar regolith simulant, JSC1 regolith simulant, and all that simulant dropped the output down to 22% of full power. They energized the system, and 5 seconds later, it was back at 98%. All the dust just got energized away. I'm sure they're quite a ways from an operational system, but it's a fascinating technique that certainly deserves more attention. And I talk about solar panels and how many solar cells you need. This was a study that described a little rover that would go along and collect regolith and process it, separate out the various elements needed, and create a substrate, and then vacuum deposit the additional layers of other elements, as well as some traces for, as contacts, and leave behind a trail of functioning solar panels behind it. Again, this study this technique has a ways to go, but it certainly is an appealing prospect. And of course, it remains to be seen whether the contents, the material content of the Martian regolith is as suitable as the lunar regolith would be. So that concludes my presentation. I'd like to thank you for your attention, and we have time for questions.
Okay, yeah. So first question here is, shouldn't there be multiple levels of airlock, primary, secondary, tertiary, and then also a place where the spacesuits are hosed down or vacuumed? This would all be for redundancy and to protect the lungs of the astronauts.
All true. I didn't mean to convey that there'd just be a single airlock, but there would be an area allocated for multiple layers of both cleaning and safety preparations. But I didn't explore that in detail.
Then another question is, would an auger or conveyor be better for regolith placement?
For regolith placement, or you mean like moving it around?
Yeah, moving it.
Perhaps. I don't, if you were going to, dig deep, then an auger would be a good way to extract some of it. But, basically I'm just moving the looser regolith around the surface to support the construction of the habitat modules.
And have you investigated algae and fungi?
I have not. There are certainly a wide variety of possible food sources. I tried to stick with things that people were used to eating, but there certainly is some potential there in terms of the productivity levels.
And another question is, can hydroponics grow a complete salad bar? Can plant waste, leaves, stems, etc., from all of these be fed to tilapia? And then he lists all the different things you'd find in a good salad bar.
Yeah, as in my presentation that was dedicated to the aquaponics facility, I talked about the fact that the tilapia will be fed a combination of food scraps, both vegetable and fish scraps, as well as duckweed. The duckweed, the protein content runs 25 to 35%, and that we believe that the only supplement to that diet will be replacement nutrients. That when you harvest the plants and the fish, that a lot of critical nutrients come with them that you have to replace, and so yes, that that would be part of the plan. Someone asked me this earlier today if I considered using human waste as food, and I said no, not out of the question, but I hadn't pursued it.
Okay, yeah, and that's all of the questions for this then.
Okay, well, thank you very much for your attention, and everyone enjoy the rest of the convention.
Okay, yeah, thanks again, Carl, for presenting.
Oh, you're welcome, Ian.
Okay.